When people talk about the Industrial Revolution, they reach for one image almost automatically: James Watt. The Scottish engineer, the steam engine, the moment, sometime in the 1760s, when a man looked at a kettle of boiling water and saw the future. The story is so embedded in popular culture that it has produced one of the most persistent myths in the history of science: that Watt invented the steam engine by watching steam lift a kettle lid and having a sudden inspiration. He did not. Watt was not watching a kettle. He was repairing someone else's steam engine, an engine that had already been running in mines and factories for half a century, and he noticed that it was wasting most of its energy by repeatedly heating and cooling the same cylinder. He designed a separate condenser to fix that problem. This is a real and important invention, but it is an improvement on something that already existed. The steam engine was not invented by James Watt, and the story of who actually invented it, what it actually did to the world, who paid the price for what it produced, and what it ultimately means. That story is far older, far darker, and far more complicated than the image of a Scottish engineer watching a kettle. Let us begin at the beginning, which is not Scotland, which is not even the 18th century. To understand what the steam engine changed, you have to understand the problem it was built to solve. In the early 18th century, Britain was running out of wood. This sounds like an environmental complaint. It was actually an engineering crisis. Wood was not just fuel, it was the primary structural material for buildings, ships, and machines. It was the source of charcoal, which was the fuel for iron smelting. And it was becoming scarce as centuries of shipbuilding, construction, and fuel consumption had stripped the forests of England faster than they could regrow. The solution was coal. Britain had coal in enormous quantities, deep underground seams running beneath much of the North and Midlands. The problem was getting to it. Coal mines, as they went deeper, filled with water. The water table was constant, and gravity was relentless. Every mine below a certain depth flooded unless it could be continuously pumped. Pumping water out of deep mines required power, enormous, continuous, reliable power. The power of horses. Hundreds of horses working in shifts, walking in circles to turn pump mechanisms deep underground. It was expensive, inefficient, and inherently limited. A horse is a finite engine. It gets tired. It needs food, rest, care. It breaks down. And no matter how many horses you put to work, there was a ceiling on how deep you could mine before the cost of pumping exceeded the value of the coal you were extracting. This was the problem. Not an abstract engineering puzzle, a real, practical, economically urgent problem. How do you pump water out of a deep mine without horses? The answer, when it came, was not obvious. It was not elegant. It was not the result of a single moment of inspiration. It was the product of decades of observation, experiment, failure, and incremental improvement by men who were trying, practically and specifically, to solve a mining problem. It happened to change the world. The story of the steam engine actually begins not with steam, but with atmosphere. In 1643, an Italian scientist named Evangelista Torricelli, a student of Galileo, conducted an experiment that would eventually make the steam engine possible. He filled a glass tube with mercury, sealed one end, and inverted it in a dish of mercury. The mercury in the tube dropped, leaving a vacuum at the top. He had invented the barometer. He had also proven something that would seem, on first encounter, counterintuitive: that air has weight, that the atmosphere exerts pressure on everything at the Earth's surface, a pressure equivalent at sea level to about 14.5 pounds per square inch. This mattered because a vacuum, a space with nothing in it, is extremely powerful. If you create a vacuum on one side of a piston, the atmospheric pressure on the other side will push the piston with enormous force. You do not need to push the piston. You just need to remove what is resisting the atmosphere. The steam engine, in its first working form, was not actually a steam engine. It was an atmospheric engine. It used steam not to push a piston, but to create a vacuum beneath one, allowing the weight of the atmosphere to do the work. Understanding this distinction is the key to understanding how the steam engine was actually invented, and it leads us to a man whose name almost no one knows. Thomas Newcomen was born in 1664 in Dartmouth, Devon, a port town in southwest England. He was not a scientist. He had no university education, no formal training in natural philosophy, and no connection to the scientific institutions of his era. He was an ironmonger, a dealer in hardware and tools, serving the mining and agricultural communities of Devon and Cornwall. But Newcomen was observant, practical, and deeply familiar with the specific problems of the Cornish tin mining industry. He knew, from his work supplying tools and equipment to mines, how badly they needed an effective pump. He had heard of earlier experiments with steam and atmospheric pressure, and over the course of roughly 15 years, from the late 1690s to around 1712, he worked, largely alone and largely in obscurity, on a machine to solve the problem. In 1712, at a coal mine in Dudley in the West Midlands, Newcomen installed the first working atmospheric steam engine. Here is how it worked. A large cylinder was mounted vertically. At the top of the cylinder, a piston fit closely to the walls. The piston was connected by a chain to one end of a large rocking beam, pivoted at the center. The other end of the beam was connected to a pump rod that descended into the mine. Steam from a boiler was introduced into the cylinder below the piston. Then, cold water was injected into the cylinder, condensing the steam and creating a partial vacuum. The atmospheric pressure above the piston, pressing down on the top, pushed the piston downward with considerable force. This downward stroke pulled the pump rod upward, lifting water from the mine. Then, the cycle repeated. Steam in, cold water in, vacuum, atmospheric push, pump stroke, over and over, as many as 12 times per minute. It was not elegant. The engine was enormous. The cylinder alone might be 8 feet tall and several feet across. It was slow. It was inefficient by any modern standard, consuming enormous quantities of coal to do its work. But it worked. It could pump water from depths that no horse-powered system could reach. Within a few years of the first installation, Newcomen engines were running in mines across Britain and eventually across Europe. By the time James Watt was born in 1736, there were several dozen Newcomen engines operating in Britain alone. By 1775, when Watt's improved engine became commercially available, there were over 100. Newcomen's engine ran the mines of Britain for more than 60 years, and Newcomen himself received almost no credit for it. Part of the reason was legal. An earlier inventor, named Thomas Savery, had patented a steam-powered pump in 1698, a simpler device without a piston that used steam pressure directly to force water upward. Savery's design had significant practical limitations, but his patent was broad enough to cover most uses of steam for pumping. Newcomen was forced to enter a business partnership with Savery, and the patents were assigned in Savery's name. Newcomen died in 1729 without fame, without significant wealth, and without a patent in his own name for the machine he had spent his life building. The pattern by now should feel familiar. James Watt was born in 1736 in Greenock, Scotland. His father was a merchant and ship carpenter. His mother was well educated and taught him at home when illness prevented him from attending school. He was a thoughtful, methodical child with a talent for making things and a tendency to become absorbed in problems until he had solved them. He trained as a mathematical instrument maker, the makers of precision tools for scientific work, and in 1757 was given a position as instrument maker at the University of Glasgow. It was not a glamorous job, but it placed him at the center of one of the most intellectually active scientific communities in Britain, and it gave him access to equipment, to ideas, and to remarkable colleagues. In the winter of 1763 and 1764, Watt was asked to repair a scale model of a Newcomen engine that belonged to the university's natural philosophy department. The model worked, but poorly. It consumed steam at a rate that made it barely functional even as a demonstration. Watt began to investigate why. He was not simply fixing the model, he was thinking about it. The thermodynamics, the energy flows, the reasons why so much of the heat was being wasted. And what he found was a fundamental inefficiency in the design. The cylinder had to be alternately heated and cooled on every stroke. Heating it with steam, then cooling it to condense the steam and create the vacuum. Every cycle, the cylinder walls were heated up and then cooled down again. The energy required to reheat a cold cylinder was enormous and was simply wasted. The solution Watt arrived at was the separate condenser. Instead of cooling the cylinder itself, the steam would be piped into a separate chamber, the condenser, where it would be cooled and condensed, while the main cylinder remained hot throughout. The vacuum would be created in the condenser, the cylinder would stay hot, and the enormous energy wasted on reheating the cylinder on every stroke would be saved. It sounds simple. It was not simple. The engineering challenges of making it work, of sealing the piston well enough, of managing the steam flow, of constructing the condenser, occupied Watt for years. He received a patent for the separate condenser in 1769, and then, for 6 years, he could not afford to build it. The story of James Watt is also inseparably the story of Matthew Boulton. Boulton was a Birmingham manufacturer, wealthy, well-connected, commercially brilliant, and possessed of an instinct for recognizing when a technology was about to become economically transformative. He had been watching Watt's work with interest, and in 1775, he offered a partnership. The Boulton and Watt partnership was, like almost every successful technology commercialization in history, a union of technical genius and commercial capability. Watt designed, Boulton sold. Watt worried about the engineering, Boulton worried about the customers. Watt was inclined toward perfectionism and anxiety. Boulton was inclined toward optimism and expansion. Together, they were the combination that worked. Their first significant achievement was not just building Watt's engine, it was extending Watt's patent. The original 1769 patent was due to expire in 1783. Boulton lobbied Parliament successfully to extend it until 1800. This extension was commercially decisive. It gave Boulton and Watt a monopoly on the most efficient steam engine design for 25 years. The monopoly was not without controversy. It meant that other inventors, some of whom were developing important improvements, could not freely build on Watt's design. High-pressure steam engines, which would eventually prove more powerful and versatile than Watt's low-pressure design, were blocked by the patent terms. The argument can be made, and has been made by historians, that Watt's monopoly slowed the development of steam technology during those 25 years.
The argument can also be made
That without the patent protection, Watt and Boulton would not have invested in perfecting and manufacturing the engine on the scale they did, and the technology would have developed more slowly regardless. This tension between the protection of inventors and the freedom of innovation did not begin with Watt. It has not ended since. Watt's engine, in its first form, did the same thing Newcomen's engine had done. It pumped water, up and down. The piston went down, the pump rod went up. Reciprocating motion, linear, vertical, powerful, and limited to a single application. What industry needed was not a pump. It was a wheel. Rotary motion, the ability to drive a spinning shaft that could power looms, mills, hammers, bellows, and machines of every kind, was the thing that would turn the steam engine from a mining tool into the engine of an industrial revolution. Watt solved this problem in 1781 with a mechanism called the sun and planet gear. The reason he did not use the more obvious solution, the simple crank and flywheel that converts reciprocating to rotary motion, was that a crank had already been patented by another inventor, and Watt did not want to pay licensing fees. So he designed an alternative. The sun and planet gear was mechanically more complex than a crank. It was also, in some respects, better.
in 1782,
Watt developed the double-acting engine, a design in which steam pushed the piston in both directions rather than relying on atmospheric pressure for the return stroke. This roughly doubled the power output for a given cylinder size. In 1784, he developed the parallel motion mechanism, a geometric linkage that kept the piston rod moving in a straight line while the beam rocked, and he was reportedly prouder of this elegant piece of mechanical geometry than of any other invention in his career. Each of these developments was significant. Together, they created a steam engine that could drive almost any machine at any speed required, with adjustable power output. By the mid-1780s, Boulton and Watt engines were being installed not just in mines, but in textile mills, in flour mills, in iron foundries, in breweries, in paper mills. The factory system, the organization of industrial production in large buildings full of machines driven by a central power source, became possible for the first time.
the Industrial Revolution
Had its engine. Between 1760 and 1840, roughly the lifetime of James Watt, who was born in 1736 and died in 1819, Britain was transformed beyond recognition. In 1760, most of Britain's population lived in the countryside, worked in agriculture or small-scale craft production, and traveled at speeds limited by a horse's legs. In 1840, Britain was the most industrialized country in the world, the largest manufacturer of cotton textiles, iron, and steel, the most extensive railway network, the most productive coal mines, the center of the most powerful empire on Earth. The steam engine did not do this alone. The agricultural revolution had already begun releasing labor from the land. The enclosure movement had driven thousands of people from their common lands into cities looking for work. The growth of banking and credit had made investment in industry possible. Legal and property rights systems had developed that allowed the returns on innovation to be captured by those who funded it. But the steam engine was the central technology, the device that concentrated production in factories, that made large-scale manufacturing economically viable, that created the demand for coal and iron and steel, that drove the mining and metalworking industries, that eventually powered the locomotives and ships that connected the entire industrial system into a single global market.
The wealth created by this
Transformation was enormous. Britain's GDP grew at rates that had no precedent in the economic history of the world. The middle class expanded. The merchant class became extraordinarily powerful. Capital accumulated at a scale that funded railways, banks, insurance companies, and imperial expansion across every continent. And the human cost was staggering. The factories that the steam engine made possible were not pleasant places. In the early decades of the Industrial Revolution, roughly from 1760 to 1850, the conditions in British textile mills and mines were, by any humane standard, appalling. Workers, many of them children, worked 12 to 16 hours a day, 6 days a week. The machinery was unguarded and extremely dangerous. Accidents were common and frequently fatal. The air in textile mills was thick with cotton dust that caused a lung disease called bisonosis, brown lung, which killed workers slowly over years. Coal mines were dark, wet, and subject to explosions, collapses, and floods. The coal dust caused black lung disease. The methane gas caused explosions. The wages were low enough that survival depended on the entire family working. Not just fathers, mothers, and children. Children as young as 5 were employed in cotton mills, small enough to crawl under the running machinery to retrieve broken threads or clean the floor. Children worked in coal mines as trappers, sitting alone in dark tunnels, sometimes for 12 hours at a stretch, opening and closing ventilation doors to allow coal cars through. Children worked in match factories, in pottery works, in glass works, in chimney sweeping. The steam engine had multiplied the productive capacity of British industry by factors that would have seemed impossible a generation earlier. The workers who operated that industry, and the children among them, received a fraction of what their labor produced. This was not an accident. It was the structure of the system. The reform movements that eventually addressed these conditions, the Factory Acts of 1833, 1844, 1847, and beyond, which progressively restricted child labor, limited working hours, and required safety measures, came slowly and against intense opposition from factory owners who argued that any regulation would destroy their competitive position and ruin the economy.
The economy was not ruined.
The children stopped working at age 5 in factories. Both things happened. Eventually, James Watt, throughout his working life, was genuinely afraid of high-pressure steam. This fear was not irrational. High-pressure boilers in the early era of steam did explode, killing people, destroying buildings, creating disasters that confirmed Watt's concern that the technology was too dangerous for general use. He argued, sincerely and repeatedly, that high-pressure steam was reckless, that the risks were unacceptable, that his low-pressure system was the appropriate technology. He was also, it should be said, aware that high-pressure engines would undermine his patent. High-pressure steam made it possible to build much smaller, lighter, more powerful engines. Engines that did not require the enormous cylinders and beams of the Watt design. Small enough to put on a carriage, small enough to put on a boat. The man who actually built high-pressure steam engines and who demonstrated their potential was a Cornish engineer named Richard Trevithick, one of the most remarkable inventors of the early 19th century and one of the most completely failed businessmen. Trevithick had grown up around Newcomen engines in the Cornish tin mines. He understood steam power practically and intuitively. He built his first high-pressure engine in 1801, a road locomotive called the Puffing Devil, which carried passengers up a hill in Camborne, Cornwall, on Christmas Eve, 1801. It was the first self-propelled steam vehicle in history. 3 days later, while Trevithick and his friends were celebrating their success at a local inn, someone neglected to check the engine's water level. The boiler ran dry. The engine overheated, it caught fire and burned. This was, in miniature, the story of Trevithick's life. He went on to build the first steam locomotive to run on iron rails in 1804 at an ironworks in South Wales, and demonstrated that a steam engine on rails could haul heavy loads. He built the first steam engine to carry passengers on a circular track in London in 1808, charging the public a shilling a ride. He had ideas for tunnelling under the Thames. He went to South America to work in the silver mines. He came back broke. He died in 1833 in a lodging house in Dartford without money for his own funeral. His colleagues in the engineering community collected the cost of burying him.
The railway locomotive.
The technology that would reshape the world in the 1830s and 1840s descended directly from Trevithick's work. The men who built the railways, George Stephenson, his son Robert, and the engineers of the railway age, built on Trevithick's demonstration that steam could move on rails. Trevithick received none of the credit. In 1829, a competition was held on the newly built Liverpool and Manchester Railway, the first railway to carry both passengers and freight using steam locomotives exclusively. The competition was called the Rainhill Trials, and its purpose was to decide which locomotive design the railway would use. The winner was a locomotive called the Rocket, built by George and Robert Stephenson. The Rocket was not the first steam locomotive, it was the best one yet built, faster, more reliable, and more efficient than any previous design. At the Rainhill Trials, it achieved a speed of 30 miles per hour, faster than any wheeled vehicle had ever traveled on land in human history. 30 miles per hour in 1829. The spectators at Rainhill reportedly found this terrifying. Some believed that traveling at such speeds would be fatal to passengers. Others believed it would make it impossible to breathe. There were predictions that the vibration would shake buildings from their foundations, that livestock near the tracks would miscarry, that the landscape itself would be damaged.
None of this happened.
What happened instead was that railway construction exploded. By 1840, there were over 2,000 kilometers of railway in Britain. By 1850, over 10,000. By 1870, the British railway network was essentially complete, connecting every major city and town in the country. Similar explosions of railway construction were happening in France, Germany, the United States, and eventually every corner of the world where investment capital could be raised. The railway did something that went beyond transportation. It created a new experience of space and time. A journey that had taken 3 days by coach could now be made in 3 hours by train. Distance, which had always been an absolute barrier, became relative, negotiable, shrinkable, manageable. The railway also created new industries: steel for rails, brick for tunnels and viaducts, glass for station roofs, telegraph lines that ran alongside the tracks to coordinate train movements, hotels and restaurants at the termini. The entire modern tourism industry traces its origin to the railway, to the moment when travel became fast enough and cheap enough to be undertaken for pleasure rather than necessity. Thomas Cook organized the first package tour, 40 local temperance workers traveling by train to a rally in 1841. The travel industry was born on a steam railway in the English Midlands.
The railway changed land.
Steam also changed the sea. The first steamship to cross the Atlantic Ocean using steam power for at least part of the crossing was the SS Savannah, which made the voyage in 1819. But it was not a practical steamship. It used its steam engines only for part of the journey, relying on sail for most of it. The engines were an experiment, not a solution. The first ships to cross the Atlantic using steam power alone, and the first to demonstrate that steam-powered ocean travel was commercially viable, were the SS Great Western and the SS Sirius, both of which made the crossing in April 1838. The Great Western was designed by Isambard Kingdom Brunel, one of the most extraordinary engineers of the 19th century. The man who also built the Great Western Railway and the Clifton Suspension Bridge, and the SS Great Britain, the first ocean-going, iron-hulled, screw-propelled steamship. Brunel understood scale. He understood that a larger ship could carry more fuel relative to its resistance through the water, making longer voyages on steam power possible. He kept building larger ships, and each one demonstrated the principle more effectively. By the 1850s and 1860s, steam-powered shipping was transforming global trade. The Suez Canal, opened in 1869, designed specifically for steamships which could navigate the canal where sailing ships could not, cut the journey from Britain to India from months to weeks. The world, in an economic and commercial sense, was shrinking. The steam engine had started in a Cornish mine, pumping water. It had moved to a textile mill in Manchester, driving looms. It had climbed onto a carriage in 1801, onto rails in 1804, and into a ship in 1819. By 1870, it was powering the entire global economy. Let me be precise about what James Watt actually contributed to history. He did not invent the steam engine. He invented the separate condenser, which made the steam engine roughly 4 times more fuel-efficient than Newcomen's design. He invented the double-acting engine, which roughly doubled the power output. He invented the governor, a device that automatically regulated the engine's speed, keeping it constant regardless of load. He invented the sun and planet gear and the parallel motion mechanism. He also, with Matthew Boulton, created the business model that brought the steam engine into wide commercial use, charging customers a fee based on the savings in horse feed costs that the engine produced, rather than selling the engine outright for a fixed price. This pricing model was clever, fair in a certain sense, and commercially decisive. And he did something else that deserves recognition. He measured. He quantified. He introduced the concept of horsepower, a unit of power defined as the rate at which a horse could do work, as a way of communicating to customers how powerful his engine was relative to what they were replacing. The unit of power in the modern scientific system, the watt, is named after him. Watt was a systematic, rigorous, deeply intelligent engineer who improved a technology by understanding it thermodynamically in a way that Newcomen, who had built it empirically and practically, had not. He took an existing machine and made it genuinely different, not just better by degree, but better in kind. That is worth honoring. It is not the same as inventing the steam engine. The distinction matters not to diminish Watt, but to give Newcomen and Savory and Trevithick and all the engineers whose names are not on the textbooks their proper place in the story.
Somewhere in the world right now,
A steam turbine is spinning, probably in a power station, possibly in a ship. The steam is being produced by burning something, coal, gas, oil, or by the heat of a nuclear reaction, and it is being used to spin a turbine that generates electricity. This is not a coincidence. This is a direct line. The power station, the device that generates most of the electricity most people use, is, at its core, a steam engine. The fuel has changed. The scale has changed. The efficiency has changed enormously. But the principle, heat a fluid, use the expanding pressure to do mechanical work, convert that work to electricity, is the principle that Thomas Newcomen understood in 1712 and James Watt refined in 1769.
The steam engine did not go away.
It transformed. It became the turbine. It became the generator. It became, in nuclear power stations, a machine heated not by burning fuel, but by splitting atoms, and then using the resulting heat to boil water and spin a turbine. We are still running on steam, and we are still paying the costs that the steam engine introduced. The carbon dioxide in the atmosphere, the gas that is driving the climate crisis of the 21st century, came in significant part from the burning of coal that began in earnest with the Newcomen and Watt engines, and that accelerated through every decade of the industrial era. The Industrial Revolution and the climate crisis are not separate events. The climate crisis is the long tail of the Industrial Revolution, the accumulated consequence of 2.5 centuries of burning carbon to power steam. This is not a reason to condemn Newcomen or Watt. They could not have known. The atmosphere's response to carbon dioxide was not understood in their era, and the quantities they burned were a fraction of what followed. But it is part of the full story. Thomas Newcomen built a machine to pump water out of a coal mine. James Watt improved it so it would use less coal. Richard Trevithick put it on wheels and drove it up a hill. George Stephenson put it on rails and carried passengers at 30 miles per hour.
Brunel put it on a ship
and crossed the Atlantic. And the world, the wealthy, connected, industrialized, unequal, carbon-saturated world that we live in, is the world their machines made. It is not a simple world. It is not a purely good world or a purely bad one. It is a world of extraordinary achievement and extraordinary cost, of liberation and exploitation, of possibility and damage, of things that would have seemed miraculous to anyone living before 1712, and things that would horrify them if they could see what came after. It is the world we inherited, and it runs, still, on the principle that Thomas Newcomen worked out in a workshop in Dartmouth. Heat water, make steam, move the world.